All right, let's get started. Okay. So last week we started to talk about machine learning and supervised learning in particular, right? And we had this very nice diagram summarizing what supervised learning is. Yeah. So in supervised learning, what we want is to learn about a target function, which is unknown to us. Now, this f function that maps the input features x to an output label y. Right? We don't know what this function is, and we want to learn about it, or rather we want to train the machine to learn about how to do this, how to do the mapping from x to y. Okay? We don't have f, but what we do have are a set of training examples, right? The so-called training data set that are generated, or that were generated, if you will, from the true target function, f. Yeah? Oh, come on. Okay. Yeah. So we have a set of training examples, and that's all that we have. We don't have the real target function, but we want to learn about the target function using these examples. Yeah? Just like we are showing a baby how to learn what a tree is. We show the baby different examples of trees. Yeah? So now you have these training examples, and you need to use this to train a machine to learn that target function. Okay? So, and this is the job of a learning algorithm, right? We have a perceptron learning algorithm that we discussed last time, one of the examples. Yeah? And this learning example, the job of the learning example is to pick a function that is close to f. Let's try to predict this f based on the training samples that you have. But you don't just predict this function out of the blue. Okay? You have to have a set of candidate functions for this algorithm to choose from. Okay? You cannot just tell the algorithm, well, any function. Okay, that's way too complicated. Okay? So what we do, we give it a set of candidate functions called the hypothesis set, h1, h2, and so on, right? Among this set of hypothesis functions, we pick one. The learning algorithm is supposed to pick one, hopefully the best one, yeah? And this best hypothesis should be close to the unknown target function f. Yeah? Okay? So this is supervised learning in a quick snapshot. And of course, at the end, we use this hypothesis function, this picked selective function, to make our prediction. Yeah? Given any new sample, now you can use it to give you a new label called the testing. Okay. Continue on along this line of recapping. We also started to discuss an example, a very special case called the binary linear classification. This is still recap. And in binary linear classification, we also have the hypothesis set. Yes?
What does that classify? Oh, is that classification?
Classification, yes. Hypothesis set, of course, is also called the decision rule. Yeah. Or the learning model. Yeah. Is that in the binary classification, we have this y hat, which is a binary output. It turns out to be the sign of this inner product, like this, right? Where this w and x, they are augmented versions, right? So these are augmented w that has a w0 in front, yeah? Not just w1 to wd, and also augmented x, which is x0, which is always equal to 1, yeah? And then this is x1, comma, comma, xd, like that. And these are commas, maybe I make it a bit clearer. Like that, yeah? And given this hypothesis set, the algorithm that we have so far is called the perceptron learning algorithm, right? that can be really summarized just very quickly by the updating step, right? The update step that says you pick any mislabeled or misclassified example. Let's call it xn with the label, true label yn, and then you update this w with this, right? That's what we have seen already, yeah? That's exactly just what the perceptual learning algorithm does. That's all that it does, really, right? As long as you have misclassified points, update your w, pick using any one of the misclassified points, right? And you keep doing this. And we saw example on last Wednesday that it works, okay? Yeah. So today we start with an intuitive explanation for why it works, okay? We don't prove it yet, but let's see why. So intuitive explanation. To explain this, we'll look at a few items, yn, in a table like that. We consider all possible cases, yeah, of yn and also w transpose xn, okay, the inner product of these two, okay, all possible cases. So what are the possible cases? Let's see. The yn can be +1, right? And then this product, this inner product, can be a plus, yeah, or can be a minus, right? When the label yn is still +1, okay? These are the valid possible cases, right? The label can be -1, and then this product, inner product is plus, label is -1, the inner product is minus. Okay? All possible cases. There's one more case, though, where this is 0, right? This corresponds to the scenario what? The point, the data point xn, is right on the boundary, right? This is right on the boundary. And in this case, we say, well, we don't care what what the label is that we assign. Let's say just +1 or -1, doesn't matter. We're going to call it a mislabeled or misclassified point anyways, right? In the PLA, in the perceptual learning algorithm, we will view this as misclassified anyways. No, doesn't matter what you label it. Okay? So these are all possible cases of what can happen to the algorithm, right? At this current step. So at this step, for this particular point, do we have correct classification? Yeah, this is this next column. So if the true label is plus, and then this product is also plus, that means what? Our estimation, remember our estimation looks like this, right? It's the sign of this product, yeah? So our estimation is also plus. Good match. We have correct classification, yeah? So this is correct classification, right? Yeah. The next case, they don't match. So it is not correct. Yeah. The next case, again, they don't match. So not correct. But the fourth case, both of them are negative. So it's a match. So this point is correct. Yeah. The last point, by definition, we say it's not correct. Yeah. Okay. So these classification results for this point. But if you look at the product between the first two columns, okay, yeah. So the inner product is a scalar, and then you scalar multiply yn, another scalar, you get the scalar, right? So the product, of course, if they have the same signs, then the product will be positive, right? If they have different signs, the product will be negative. So you have plus, minus, minus, plus, yeah, and then this is just 0. Okay, and turns out that we say that these two and also this one as well, these are misclassified, right? Okay. We have correct classification for this point only if that product is positive. Yeah, everyone okay so far? Yes. Oh, when there's a match of the true label and the predicted label. Remember, this predicted label is y hat, right here, right? Y hat is the sign of the product, yeah? You want the predicted label to be the same as the true label. Then it's a good match, right? Yeah? Then it's a correct classification. So if they have the same sign, then it's a correct classification. So if the same sign, then the product is positive. Okay? Okay? Yeah. So our objective really is to make sure that every single point, this product is positive, right? Then we all set. Then there is no error. Yeah? We make sure that every single point, this product is positive. Yeah? Now, then let's look at this a bit more carefully. Yeah? But let's write it down so that you have in the notes. If this point is correctly classified, then we know that this product has to be positive. And if this is misclassified, this product is less than or equal to 0. Okay? So now let's see what happens when we do the perceptron learning algorithm update. So suppose you have a point that's misclassified. So this point is misclassified. And we're going to write this as the new one after updating is equal to, just based on the rule that we have for the perceptron learning algorithm. We do this, right? Yeah, that's how we update to a new W. Okay? Yeah. So now let's take a look at the product, the last column for this new W. What happens? Okay? Let's look at the product for the new W. So Ym times W new transpose times Xm, right? Of course, I can substitute whatever that's above in here, W plus Ym Xm transpose times Xm. Yeah? And we just break up this sum in the middle, multiply them out. Yeah? The two terms, multiply them out. We have Yn W transpose Xn plus, for the second term, we have Yn times Yn, so Yn squared, right? Yeah? And then we have M transpose times Xn, which is simply the 2 norm square of Xn, right? Yeah? Everyone okay so far? Yeah, everyone with me? Yes? That's right, yeah, Yn is correct. No, Yn is always the correct label. In the perceptron learning algorithm, Yn here, this step is always the true label. Yeah? What? Yeah, this one, the sign of this column would be y hat. Yeah, the sign of that is y hat. But we are not using y hat here, right? Yeah. Okay, everyone's okay so far? Yeah? So now you see that we already have the previous term showing up, right? The previous step, the product showing up here. Let's see, this new one is an improvement or the opposite of improvement, yeah, over the OW. Okay. What do you think? Well, this Yn squared is always greater than equal to 0, right? Well, it's actually more than that. It's always plus 1, right? Because Yn is either plus 1 or minus 1, yeah? The square is always just equal to 1. How about this 2 norm of Xn? Is it positive, negative, non-negative? It's a square, okay? First of all, it cannot be negative, right? But can it be 0? Can it be 0? Remember, our xn is the augmented xn. Yeah, the first term is 1, right? So the square, the norm square of this cannot be 0 either. So it's strictly greater than 0. Okay? Strictly greater than 0. Yeah, because this is because of augmented form. Yeah. We have xn for the first term, xn 0 equal to 1. Yeah. Okay. So that's why. So therefore, the second term is strictly greater than 0, and therefore, we have this relationship. The new product is strictly greater than the old product. Yes? Say again? Oh, okay, because yn is either plus 1 or minus 1, right? Yeah. Okay. So we strictly push this point to the positive side, right? The product will push it to the positive side. And remember in this table, we want the points to be positive, right? Yeah. So therefore, in every step, when we update, when we pick a misclassified point, we want to update the W, we're pushing this misclassified point closer to a correctly classified point. Yeah? It's strictly better, okay? So for this one, it's strictly better. Yeah? So it's a strict improvement. For this point, xn. Yeah? Okay? And in a way, that explains why we do what we do using the perceptual learning algorithm. Okay? Yeah. Everyone convinced that we make a strict improvement every time? Yeah? Okay. Now, there's a caveat here. We make strict improvement only on this one point, the misclassified point. In fact, there's no guarantee that this new W does not make the other points worse. Okay? So therefore, this is only intuitive explanation why it works. Okay, this is not a formal proof. It cannot be, because we cannot guarantee that for the other points they are better. Yeah, so just make a note about this, be careful, yeah? But could also cause, say, new misclassification, yeah? New for other points. Examples. Yeah. Okay. To properly show that the perception learning algorithm works, you have to really have a different proof, a more rigorous proof than this intuitive explanation. And this, in fact, was given first by someone called Rosenblatt. Yeah, very good. So sometimes this is called the Rosenblatt's perceptron. And this was done in, guess what, 1957, a long time ago. As I mentioned before, artificial intelligence and machine learning, these are not new concepts. People have been thinking about it for a long time before this. The only problem is that at the time, they did not have the computation power to do what we could do today, and they did not have that large amount of data that Google has these days. Yeah? So that's why they were not able to do a lot of the more interesting things, but then they're building a foundation. So where we are right now was really based on the foundation that these people laid a long time ago. Yeah, gradually we built up the foundation until we have the computers and the data to do what we can do today. Yeah. So Rosenblatt showed in a paper published in 1957 that indeed, given a linearly separable data set, the perception learning algorithm converges in a finite number of steps, yielding an error that's 0. Yeah, it correctly classifies everything. Linearly separable data set. The perception learning algorithm, let's say, terminates in a finite number of steps, finally yielding remember our notation for the training error, right? The so-called in-sample error, yeah, equal to 0, yeah, meaning that there's no misclassified points. Okay. And the proof was given in that paper. It is actually part of the textbook's homework problem 1.3. I'm not going to assign it because I view this as optional. There are a few interesting steps. For those of you who are interested in this kind of stuff, it's actually quite stimulating. But for the rest of you, if you are not, don't care about how to prove it, that's okay. But it will be interesting to know that the maximum steps until convergence, turns out you can show it, is upper bounded by this value, r squared over gamma squared, where r squared pretty much indicates how large the space is for your data points. So more precisely, r is defined as the maximum size of the 2 norm of your data points, of the training points. So how big those data points can go, yeah, those vectors can be. And then this gamma is approximately equal to what we call the margin of separation between the pluses and the minuses. Okay? Remember, we assume these are linear separable points, right? So two sides, pluses and minuses. How far away they are. Okay? This gamma approximately represents that. Okay? The margin, quote unquote, of separation. We're going to properly define this later when we study the support vector machine, okay? And because at that time, this margin of separation becomes important. But for now, just suffice to say that maybe this thing is actually, by definition, equal to this thing. This, the 2 norm of some W star, which is the optimal solution, and then divided by this yn, this W star transpose xn, like that. I just want to show you this because this product shows it again. I just want to remind you that this product actually is important. Okay? Yeah. And again, we'll see this form very often when we study SVM. Yeah. And here, of course, I have to define W star. It is any optimal solution. Set of weights. Okay. So you can notice that this maximum number of steps is a function of these two ratios, right? So the larger r is, the larger space that you have to place the points takes longer time, many more steps. Okay. Also, if the separation of those points is narrower, gamma is smaller, you also take more steps to search for this line. Okay, which makes sense, right? If the gap is narrow, it's harder to find a line. Yeah. Okay. So intuitively, this formula makes sense. But you can prove it, but we don't have to do it in this course. Yes. It's the maximum number of steps before the PLA converges. Yes. Well, yeah, if you know you have read this ahead of time, then yeah. This is almost the exact margin, except that this one should not be augmented. If this one is not augmented, then it will be exactly the margin. Okay, but we'll get there when we look at SVM. Yeah. Perceptual learning algorithm.
Sorry, for the PLA, you mentioned that for each updating step, that works for only one of the
Yes,
data.
that's right.
So I wonder, until it gets to the point that the error would be 0,
Mm-hmm.
is there any trend that the algorithm gets better and better, or is it?
No. Yeah. Good question. It goes up and down. Yeah, goes up and down. No guarantee whatsoever. But the guarantee is that after these many steps, it will be 0. So then we're all done. Okay. Now, here I mentioned this is any optimal set of weights. Of course, by implication, that means we have multiple optimal solutions, right? Which, of course, is true if you have two sets. The line that you can draw, many lines you can draw, right? Let me just write this down as a remark. the output of the perception learning algorithm is not unique in general. In fact, there are infinitely many solutions. So let's say something that looks like this. Okay, and then the minus is here, like that. I can have a line. Let's say if I can draw like that, okay. Or I can have another line. Let's say, like this. Okay. Both of them would be a valid solution for the perception learning algorithm, right? Both lines will give you a 0 classification, misclassification. Okay, so not unique. You have a question there? Yes.
Are we done with the proof?
We did not prove it. We just say that that's the kind of the outcome of the proof. Okay.
Oh, so basically,
it's optional, so I'm not going to talk about it here.
Thank you.
Now, if you have so many different solutions, is there a better solution than the other? For example, these two lines, red and blue, which one is better? Okay. Which solution, which one is better? Yeah. Yeah.
Would it be the one that separates them the most, so the biggest
Mm-hmm.
distance between the closest data point?
Yeah. Why would you want to choose that one? So the red one here, right? The red one would be better, you're saying, yeah?
Because you probably have like higher confidence that it's
Mm-hmm.
correct. So if you get more data points, you have a higher confidence that that line will separate that data point from.
Yeah.
It will classify the data point correctly.
Yeah. Okay, this is one answer, right? So it turns out that it really depends on what you mean by better. Okay, if you only care about your training error, so E in, then both lines will give you 0 E in, right? Both of them give you training error 0. So both of them are as good. Any one of the solutions will be as good as the other. On the other hand, if you care about E out, the so-called testing error or out of sample error, now you have to worry about in the real life, I don't get just these points, right? I get new points. And those points may be noisy and so on, okay? A better line would be a line that's maybe right in the middle, right? Instead of this blue line, which is so close to the other side, if there's any noise, that one point, because of noise, jump to the other side, then I misclassify the point, yeah? So to reduce the testing error, or more fancily speaking, to reduce the generalization error, we want to pick the red line rather than the blue line, okay? That's another story that we will go through again later when we talk about SVM, okay? For now, we don't care. For now, we just say, yeah, any line is as good as the other for the training E in. Yeah? Okay, everything comprehensible so far? Okay. All right, so now, so far all of this is about separable data sets, yeah? But we know in real life, most of the time we have to deal with not linearly separable data sets. What do? And one way to extend the PLA is to use what's called the pocket algorithm. It's a very simple idea. Once you know what it is, you'll see, oh, just trivial almost, okay? So the pocket algorithm extends the perception learning algorithm for data sets that are not linearly separable. So in that case, if you look at E in over time, T is the iteration, E in, yeah. The PLA might give you something that looks like this, you know. It one step you improve and sometimes you don't improve. If it's separable, then overall, at the end, you are confident that at the end it goes to 0. Yeah? But when it is not separable, it never really goes to 0. Okay? It goes up and down like this. Yeah? Because it does not converge to 0, right? It just keeps fluctuating, which is terrible, right? If you just stop here, you get a pretty bad answer. Your E in is pretty large. Okay? So the idea is not to stop in some arbitrary position and say that's my solution. Yeah? Rather say, what is the current best one? Or say, well, this one actually pretty good, right? This one is at the bottom. I should just keep this solution as my output. That's all that there is. That's what the pocket algorithm means. You have a question? Okay, all right. So keep the best weight vector or solution, let's say W, up to iteration T in the pocket. Okay, that's why it's called the pocket algorithm. Yeah? Okay. Almost kind of trivial solution, right? So if we write it out, just for the sake of having something formal, we'll say in the first 0 step, initially, we'll just pick a certain time horizon that we will stop. Percent T, let's say, yeah. But instead of just stop at T and then use that final solution, we simply set a pocket weight or pocketed weight vector, the first wave vector, yeah. Let's say, call it W hat, yeah, to W0 in the initial wave vector in the perception learning algorithm, yeah. And then, of course, now you can iterate T equal to 1, 2, to T. You do the following. You're going to run the perception learning algorithm for one updating step. To obtain, say, something, let's W of T, yeah, at the T step. Of course, now you evaluate how good this one is. Evaluate E in based on this new weight vector. And if it's better than your old one, then you keep it. If it's not, then you throw it out, right? Trivial algorithm, really. If this is less than E in of what you have in the pocket, yeah, W hat is what you have. Now you set the pocket one to be the new one. That's it, yeah? And at the end, you're going to return, after this for loop is done, you're going to return whatever you have in your pocket. Yeah. So this part should be, I guess. Very simple algorithm. Yeah. And of course, it is a heuristic, right? It's absolutely no guarantees. As we mentioned, when it's not linearly separable, the problem is NP hard, right? So you should not expect any guarantee, really, unless you have more than exponential time, or unless P equals to NP. Yeah, heuristic. However, numerically, we know that it performs pretty well. Yeah, performs well in practice. So let's take a look at an example, which is from the textbook. So I'll just show textbook example of on classifying two things, the handwritten digits 1 and the handwritten digits 5. Okay, so let's take a look. Yeah. Everyone finish copying before I go to the other slide? Yes?
Sorry, what does that square bracket in?
Oh, just to indicate that it is the row in the do part, that's all. I should have shifted it to the, you know what?
Oh.
I can shift it a bit more. It probably should have done that. Although I wrote it so much to the right-hand side, I don't have a lot of room to shift it. That's all.
Will you repeat those steps, or?
Oh yeah, it's a for loop. It's a for loop, yeah?
It's a loop.
It's a for loop, yeah. Yes. A similar algorithm? There is logistic regression. We're going to go there next week. And SVM, of course, SVM, but when we talk about it in the second half of the course. Okay, so let's take a look at the textbook example. So we have seen this before in the first lecture, right? Handwritten digits. You want to train computers to recognize handwritten digits like this. Yeah? So you're given the training examples, which are these digits with a label. Yeah? So one direct way to do it is to say that, well, this pixel, this image is a 16 by 16 pixel image. So altogether there are 256 pixels, each one of them. So each pixel has an input, you know, x1, x2, and x3, and so on. Then you will have a vector that looks like that, right? x256, and then plus 1, yeah, the augmentation, x0, okay? And then you have a corresponding wave vector like that. But very often we don't do it because these pixels are not very structured, and it's a very high dimensional. It's hard for machine to learn, okay? At least in the old days when the machines are not so powerful. Nowadays, this is even, you know, 256 is nothing. Right? We're talking about millions upon billions of input values. But let's say that's a lot, okay? So a common thing people do to reduce the size of the input is to extract features, okay? Feature extraction, yeah? In this example, we extract two features out of this image. One is the intensity. So that's how dark the image is, okay? You sum up the pixel values, take the average, divide by 250. That's intensity. Symmetry, of course, you can just set a line like that and measure two sides, how different they are, okay? So in this example, these are the two features that you have extracted. Now, every single one of these images can be represented by a vector of x1, x2, right? Plus augmentation x0, okay? So now we have a d equal to 2 case, two-dimensional example now, and now we can very well illustrate the two-dimensional example on the board, on the screen, yeah? So that's why we choose two features, yes? X0 is the augmentation. X0 always equal to 1. Remember, we have the augmented form, yeah? Very beginning, okay? So now if you look at between 1 and 5, okay, these two extracted features, intensity and symmetry. So it turns out that it's missing in the textbook, but this is x1, this should be x2, okay? The intensity on this way, and then symmetry on that way. You see, the red dots, they represent 5. The blue ones is 1. Why is that? If you look at the intensity, the red ones tend to have a high intensity, right? Yeah, because there's more dots to write a 5 than a 1, yeah? In terms of symmetry, the 1 has a higher symmetry, right? In general, yeah, looks like more symmetrical, okay? So that's why these are the many different 5s. Those are many different 1s, right? You have to show the computer many examples, right? For the computer to learn. Now, with our big brain, we look at this, we immediately know where to draw the line, right? Because our brain is well trained. Since we were a baby, we have been trained to separate things, how to recognize patterns. human beings, if we are not good at anything, we're good at recognizing patterns. Yeah. So we know there. The question is, how do you teach computers to do it? How do we train a machine to be able to see that right line to use? Yeah. So if you run the perceptron learning algorithm, you will get this. Yeah. Suppose you run it for 1,000 steps. Okay. This green line will be our E in the training error. Okay. E out is the test error. For now, we can ignore it. Okay. The test error in general is worse than our training error. Okay. But later we'll talk about how to make this closer. Yeah. Okay. But for now, let's just worry about E in. You see that E in goes up and down, right? Because clearly this is not separable, not linearly separable data set. Yeah. So E in, there's no hope can converge to 0. Okay. So just keep going up, down, up and down. Yeah. And in that, if you stop at 1,000 and say, okay, that's my final solution. Okay. That will be the line. Again, with our big brain, we see that that line is not the best line to use. Yeah. In general, you don't know when to stop, right? If you just run PLA, when do 1,000 is good, 10,000 is good? We don't know, right? If you just stop here, that's the line that you get. Yeah. Yes.
Do we have to be like 100% accurate in this case? Like,
well, we want to be as accurate as possible. It's impossible to be 100% accurate, right? Because E in can never be 0. This is not linearly separable. We will never be 100% accurate. Okay. Yeah. We just want to minimize E in. Yeah. Okay. Yeah. So yes. That's why we want to minimize E in, right? The training error. Want to minimize the error as much as we can. Okay. But if you see, this one is actually not a good point. But if you look throughout your history, right? Well, it's that this point is pretty good, right? If I had remembered what that line was, I should use that line instead, because that line gives me this E in lower. That's the whole idea of the pocket algorithm, right? We want to, grab this point somewhere. Yeah. So that's PLA. If you do it, then you always keep this the minimum. Then it's this one. Yeah. So yeah, you keep this in the pocket, and then that's what you get throughout. That's the best one you have. And if you see the final answer, this one is the best one for the within the first 1,000 iterations. Now, if you keep more iterations, you might further improve this. Who knows? Yeah, MPR problem. We don't know what will happen at the end. Yeah, so you just have some general estimation about how long you need to take, and then you just stop there. Yeah, it's so-called hyperparameter tuning, what T should be. Yeah, okay. But anyway, with our big brain, we see that this line is pretty good, right? Already. Yeah, although maybe a bit slanted down, might be even better. Yeah, but yeah, good enough, right? Okay, so that's the example on pocket algorithm. Now, one more thing I want to mention is that so far we have been talking about binary, yeah? But we see that's only allow you to separate 1 and 5, right? But we have 10 digits. What do we do? Okay, so, well, if you already have a binary classification algorithm, can you use it to classify 10 different digits? How do you do it? Yeah, very good. Yeah, so that's good. So let's write it down. So this is called multi-array classification. Can be implemented. Whether you should implement it that way is a different story. It can be implemented by a sequence of binary classifications. Right? So I send this digit image in. Well, let's start from 0. Right? You ask, is it a 0 or not a 0? Yeah. If yes, it is a 0, then of course your output label is 0. If it's no, then you continue, right? You continue. Then you ask, well, is it 1? Yeah. And if yes, then you output, well, is it 1? If no, and then you ask, well, is it a 2? Yes, then you say, well, output is 2. No, and then so on and so forth, right? Yeah. In this case, if you do this, well, you just need 10 perceptron, right? That's fine, right? We know how to build a perceptron. Just build 10 of them to separate these numbers. It can be done, although this will not be the most efficient or not most effective. Yeah, not most efficient, and also not the most effective. Wow. Any reason why? Okay. 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 Yeah, but well, you have 10 classes though, right? Do you have a choice other than that? Yes. Huh? That's right. Yeah, because not easy to separate 0 and non-zero and so on when you have all these other digits with scattered around your space. That's another thing. Maybe you. Maybe, yeah. Well, y is equal to 9, let's say. Yeah, okay, we don't have 10, 9. Yeah, we don't know, right? Which order we should use, for example. Yeah, something else? Yeah, that could probably. Also, there's another thing. Maybe someone.
I was gonna say because like the features that you're extracting
Yeah.
are not compared in the same way. So like when you're separating zeros and ones, for example, it's gonna be very different from when you're separating fives and ones.
Yeah. You don't know, right? Yeah.
For example, you can have an image of 9, but it's written very similar to a 0.
Mm-hmm.
Then because this thing is being connected.
Could be. Yeah. That's right. Yeah. It could be a trouble. Another thing that no one has mentioned yet is that you don't have to separate this one by one. You can separate into 2 5 digits and another 5 digits and say, are they separate or even numbers or odd numbers? It could be one way, right? Well, might not be the best thing to do, but maybe there's a good way to separate them. Do kind of a binary search kind of thing, right? Separate them in half and then half on those half, right? It could be more efficient. Who knows? Yeah. So basically the point is that this is not the most efficient way or effective way to do it. And that leads to, but then this idea here is that still this is one way to connect the perceptrons together to solve a more complicated problem. And that's the idea of a neural network. And in a neural network, we don't do it this way. Yeah? We do it in a more sophisticated way and we just train the neural network, train the connections. We don't know how to build the connections. We just use our training examples to train those connections and how to connect the different perceptrons together. Yeah, okay? And that will be a topic maybe in 3 weeks. Yeah, just a bit of a preview for that. Okay. All right, any questions? Yes.
If our data set is like really, really big, okay?
Yeah.
And you yourself, and it's also like, let's say, right, like 10 degree data sets, right?
Yeah.
If you yourself can't tell just straight off the bat if it's linearly separate or not,
Yeah.
how do you choose the time so that the model can have a full chance of finding the lowest,
Yeah, you don't know. This hyperparameter testing is always difficult. This hyperparameter testing to know the time that you need. You just have to, very often you have to wait until it gets low enough for you. Yeah, it's very hard. It's a hard problem. All right, I'll see you tomorrow, yeah?